3, 2, 1.
Cool. Hello, everyone. Welcome to our first Tech Talk of URTC 2020. I'm here to introduce Professor Vivienne Z. She is an associate professor in the MIT's Department of Electrical Engineering and Computer Science and leads the Research Lab of Electronics Energy Efficient Multimedia Systems Research Group. Her group works on computing systems that enable energy efficient machine learning, computer vision, and other things that have a wide range of applications, including autonomous navigation, digital health, and the Internet of Things. Today, she is here to present energy efficient computing for AI and robotics. So let's give a warm virtual welcome to Professor Vivienne Z.
All right, thank you so much, Fiona. And it's really great to be here. I hope you guys are all doing well. So I'm really excited to share with you some of the work that we've been doing at the intersection of computing for AI and robotics, which are very exciting applications. I noticed that there's a lot of interesting related topics being presented at the conference. So hopefully this is a good primer for that. I should mention that the work I'm going to present today is in collaboration with various folks. And in addition to my students, I also collaborate with Surtesh Kerman, Joel Emmer, and Thomas Helt, who are also professors at MIT. And if you want to know more about our research, our group website is shown here. And we also give research updates on our Twitter feed. So next slide, please. So we know that, AI and robotics is, super interesting, but a lot of the computing for these applications currently happen in the cloud, but there's a lot of compelling reasons why we might want to move the compute from the cloud to the edge itself. So the first reason is communication. So often we might not want to be so reliant on communication in order for these applications to work. One reason is that if we really want these applications to be deployed worldwide, we might not want to be so reliant on a large communication infrastructure, which is not readily accessible around the world. Next, click. Another reason is privacy. So often, in particular, when we talk about AI, we deal with sensitive data, for example, health data, and you might not want to send all of that data for privacy and security reasons to the cloud. So it might be better to bring the compute to where the data is at and keep it local on the device itself. Another click, please, another advance. One more click, yeah, thanks. And so finally, another reason is when we start, go back for a second. So another reason why we might want to do computing locally is if we think about interactive applications where you interact with the world. So for instance, in robotics, you need to, react to changes in your surroundings. And there, latency is really critical, right? So for instance, you might not have enough time. Imagine like you're a car careening down the highway. You might not have enough time to, wait for the data to be sent to the cloud, processed, and come back. So instead, to avoid all that communication time, you might want to do the processing directly within the robot itself. So for these three reasons, it's really important to kind of move the compute out of the cloud and into the edge device itself. So now next slide, please. And so the main challenge for this, though, is that when we do move the data, move the compute out of the cloud and into the edge, into, for example, the robots, is the power consumption. So for example, if we look at self-driving cars, they often collect a huge amount of data, so 6 gigabytes of data every 30 seconds. And just to process that data, this is the sensor data to understand where they are in the world, can consume thousands of watts of computing power. Right, and this generates a lot of wasted heat, and sometimes you need to have water cooling to keep the heat down. And you can imagine being in the vehicle, you don't want to get so hot as well. So that can be a big challenge. Next slide. And you can imagine that this is even a more bigger challenge when we start shrinking down the size of the device. So for example, if you think of a robot, which is the size of the palm of your hands, or maybe even your smartphone, right? So whenever you have these portable devices, these constraints are going to be much more challenging. One of the reasons is that they often rely on batteries, and the battery capacity is often limited by the size, weight, and cost of the device. One advance, please. And then the next reason is that if we look, another advance, please, sorry. If we look at existing embedded processors that are used to do a lot of these AI tasks, they often consume higher power than what we can actually budget for these portable devices. So you can imagine another version of a portable device is a wearable device where you're very sensitive to heat. And often in these types of devices or even handheld devices, because of the heat dissipation, you're limited to under 1 watt of power. right? So these are tight power constraints which existing processors can't meet. Next slide, please. And in the past, so what we would do is we would wait for transistors to become smaller and more efficient. This is primarily driven by Moore's law and Dennard scaling. So Moore's law would give us faster transistors, and Dennard scaling would give us more energy efficient transistors. Can we get a click, please? But what we've noticed, another click, is that over the past, over the past 10 years, basically this trend has slowed down. So the number of transistors are not getting faster and they're not getting more efficient. So we need to really turn to another approach of doing this. Next slide. So what we need to do is we need to take a cross-layered approach. If we want to have energy efficient AI and robotics, we need to look across the entire stack to make it more energy efficient. So one thing is to look at the algorithms perspective. Now, in the past, people have designed algorithms primarily to improve the quality of results. So for example, in the case of neural nets, you'd try to really increase the accuracy. What we think is really important is that in addition to looking at increasing the accuracy, we should also consider the energy or the computational cost as well, and jointly optimize for this objective. Advance, one click, please. The next is that we want to rethink the hardware itself. So since the hardware is not becoming more efficient, we need to redesign the computers from the ground up to be more efficient as well, and really specialize them for specific tasks. And this might mean coming up with new computer architectures, which make us think about how we should organize the memory on these computer chips, and how can we realize these computer chips or these new specialized computer chips in actual circuits. One more click, please. And also, finally, we want to think about how the cost of computation is integrated into the actual system itself. So if you're thinking about a robot, for example, you might want to think of the interplay between the energy of the compute, the sensing, and the actuation, because the overall goal is to improve the energy efficiency of the full system itself. Next slide. Now, if we're going to, focus on energy efficiency and power cost, what we should really ask is, where is the power and energy going? And as it turns out, it's actually dominated by data movement. What do we mean by data movement? Well, we mean that, you can do a multiply and add, and that consumes a certain amount of energy shown in the blue on this plot. But the cost to actually bring the data to the input of the multiplier, for example, and then read it back out, which is shown here in the orange, is actually going to be much more energy than doing the multiply itself. So moving data in and out from, let's say, the memory to the multiplier add, and then reading it back out and putting it back in memory is going to be much more expensive. So data movement actually dominates the power consumption. And if you look at the last orange line there, the further away the memory is, so for example, if you have to go off the chip itself to what we call DRAM memory, it's going to be even more expensive in terms of energy consumption. So if we really want to reduce the energy consumption of these systems, we really need to focus not on just the computations that it does, but also how we move the data around the actual system as well. All right, next slide, please. Now, the challenge, though, is that if we start thinking about autonomous navigation, it actually uses a huge amount of data. So for example, if you want to do what we call semantic understanding, which is basically given an image, can you understand what each of the pixels represent? For instance, does this pixel represent a person? Does it represent the grass? Does it represent the sky? That can be computationally pretty expensive. First of all, you often want to do this at very high frame rates. So if you're capturing these images, you want to capture them at high frame rates especially if your robot's moving very quickly, and so your environment is changing. You might want to do them at large resolutions so that you can see objects that are far away. You can imagine, in this example, the person who's furthest away is going to have the fewest number of pixels. So we want to have large resolutions to be able to see them adequately. And then often you might need to also expand the data in order to do things like support different scales. And often expanding the data, for example, building things like an image pyramid shown in this image below, would increase the amount of data that you have to process by 1 to 2 orders of magnitude. Click. Another challenge that we have in autonomous navigation is what we call geometric understanding, where you want to understand not just what the pixel is, but how far away it actually is. So you can imagine, for example, if you're navigating through a space, how can I construct like a 3D map of the space that I'm navigating? And you can imagine the longer I navigate for, the larger the size of the map. And again, that's going to be a huge amount of data that you need to move around and process. So that's one part of the challenge. Next slide, please. So in one of the first tasks that we want to consider when we're talking about autonomous navigation, and we're going to talk about how we can make this more efficient, is the task of visual inertial localization. And the goal here of visual inertial localization is to determine the location and the orientation of the robot in a 3D space based on images from a camera that might be mounted on top of the robot, as well as an IMU that's located on the robot. So the IMU has a accelerometer and a gyroscope. And so if you look at the video on the upper right-hand corner, that's the video of the camera on top of the robot itself. This is what the robot sees. And based on that and the IMU, it's estimating, as you can see, the location of the robot in the 3D space, right? So this is first, as I mentioned, the first key thing you need to do in order to navigate, you need to know where you are. This is also a really important feature for applications like virtual reality and augmented reality. If you're navigating in an unknown space, you might also need to build a 3D map, as shown below. Next slide. So the key challenge is that we want to be able to do this in a very energy efficient or power efficient way so that we can mount it efficiently on various robots. And so indeed, we were able to do this task of localization in under 25 milliwatts. This is a chip that we called Navion. It's one of the first chip that performs all, complete visual inertial odometry. It does all of the processing in the front end of the camera. So all the pixels that come in, we process them. We look at feature detection, tracking, and so on. We also, process data from the IMU. And then at the very back end of the system, we need to fuse these different modalities of information together to estimate the 3D space. And so you can see that the chip Navion is quite small. It's 4 millimeters by 5 millimeters. It's smaller than the size of the quarter, and you can mount it on a small drone. And in terms of the energy cost, it consumes 600 to 1,500 times less energy than a mobile or desktop CPU, right? While at the same time, if you look at the graph below in terms of things like the camera rate, it's still able to process up to 171 frames per second. So it still maintains high throughput. So how does it actually do this? Well, the key thing, again, is how we efficiently deal with memory. So next slide, please. So the key thing is that, first of all, we want to integrate all of the processing that we have to do to figure out where we are in the 3D space, but to integrate it all onto the chip itself. Because as we mentioned, moving data on and off chip can be orders of magnitude more expensive than, moving data on chip and doing the computation itself. So first, everything is integrated onto the chip. The next thing that we want to do, though, is that's a huge amount of data. So how can we reduce even the data movement on chip? So click, please. So the first thing that we want to do is that any data that we store on chip, we are going to compress it. In particular, when we're processing the camera images that come in, we're going to do low-cost compression on those images to reduce their sizes. Now, the key thing is that we need to make sure that it's low cost, because you don't want the cost of doing the compression to outweigh the benefits of the compressed data. Click. The other thing is that in the back end, there's going to be a lot of sparse data, both structured and unstructured sparsity. So sparse data meaning data with a lot of zeros in it, so it's not densely packed. And so then we can exploit this sparsity as well to reduce the amount of data that's being stored. So for instance, you're only going to store the non-zero values and their locations. So click again. So all in all, by exploiting compression and sparsity, you can reduce the overall memory requirement for this very complicated task of visual inertial odometry down to under a megabyte. And this is all stored on chip, so around 854 kilobytes. And that's really how we're able to significantly reduce the power consumption all the way down to 25 milliwatts. Next slide, please. And so where can this be applied? Well, there's actually a whole range of robots out there that we call low energy robotics that actually consume very little energy in terms of actuating and where computation dominates. So for example, on the left-hand side, we can see blimps, for example, which doesn't take too much energy to stay up in the air, but making decisions could dominate that. You have also miniature satellites that can drift out in space, and then small foldable origami robots that also don't require too much energy in terms of actuation. So having efficient computing can play an important role in these types of low energy robots. Next slide, please. So this is just one small snippet in a range of work that we've been doing in the area of low energy autonomy and navigation. So I actually have a group that I lead with Surtesh Karaman, who's another professor here at MIT. And we've been looking at various aspects of low energy autonomy and navigation, from things like motion planning, robot exploration, depth estimation, and then localization and mapping, which we just talked about. So if you're interested in learning a little bit more about this area, both from the hardware and the algorithms aspect, I invite you to visit the lean.mit.edu website. All right, next slide. All right, so one of the things when we talk about AI that we must talk about is deep neural networks these days, right? So we know that deep neural nets are really giving state-of-the-art accuracy on a wide range of tasks, and they're also widely used in robotics. So for example, we have computer vision, where neural nets can help you recognize objects in a scene. We use it these days for speech recognition as well. It can also be used for things like gameplay, and although there's a lot of exciting medical applications as well. Can we click, please? So if we click, so one of the big challenges for deep neural networks is that while it gives, huge state-of-the-art accuracy for these range of tasks, the main challenge, though, is that it requires several hundred billions of operations and weights. In these cases, actually, most recently, even billions of operations and weights to do the computation itself. And so when you kind of think about that type of computation and you compare it to something that we all widely use, for example, video compression, we have that all on our phone these days. We're talking about the fact that deep neural nets are going to be at least 100, if not more complicated than video compression. So if we really want, this type of technology, deep neural networks, to be as ubiquitous and as widely used as video compression, we really have to think of ways to make it more efficient. Next slide. So there are some properties of a deep neural network that you can leverage and use to your advantage. The first is, those of you might be familiar with it, it's a bunch of multiplies and accumulates, and those multiplies and accumulates can happen in parallel. So high throughput or high speed is possible. Click, please. And so the main challenge, it should be no surprise to you guys all, is that it's the memory access that's really the bottleneck. So for every multiply and accumulate you do, there's going to be 3 reads and 1 write. So there's a 4-to-1 ratio in terms of memory access to compute. Click, please. And the main issue is that if this is accessed, for example, from off-chip DRAM, each of these accesses are going to be orders of magnitude more complex. So if you take a well-known network like AlexNet that has 700 million max, you're talking about 3 billion DRAM accesses to support that. Next slide. Right. However, there's some opportunities, what we call data reuse opportunities, meaning can I read some of this data once and then use it for multiple operations? So then I don't have to move the data around so much. Right. Next. So one opportunity for data reuse and input data reuse is what we call convolutional reuse. So for those of you who've played around with convolutional neural nets, we know that the same inputs and weights are going to be used multiple times in a convolutional manner. Next, please. We often also apply multiple filters on the same input image. So that means that each image, or so each pixel in the input image can be reused multiple times across the different pixels. Next, please. Yeah, and then often if you process more than one image at a given time, that means that you're going to have what we call filter reuse, which is a weight and the filter can be reused multiple times across the different images. So there's a lot of these exciting reuse opportunities. So you read once and use it multiple times. Next slide, please. And so what you want to do is you want to come up with interesting hardware architectures that allow you to exploit this type of reuse. So one idea is that you want to have small memories that are close by to where you're doing the processing, and the energy is going to be really low to access this very small memory nearby. But the problem, of course, is that the amount of work you have to do is going to be very large. So if you have a small memory that's only, let's say, under 1 kilobyte of memory, but you have hundreds of millions of weights and activations that you have to process, the question is, how can I break down this very large neural net into small pieces so that I can reuse it at this small local memory? And what's the order of which I want to pass through the data? So one way that we sometimes think about this is if you have a huge amount of work and you can only bring a small bag to school to do work, what kind of data, what kind of things should you store in your bag to get the most work done during the day? right? And then if you can, if you can update it, how frequently would you update? Like, what is the order in which of the chunks that you would process? And so the idea here is like, how to take this large amount of data that you need to process and break it up to small pieces and process them in different orders. You might also want to consider, how is the data distributed across different processing elements, which is shown here in PE, which process things in parallel. So for example, if you're going to school with a friend, what should they carry in their bag? And maybe you can exchange data, and that's much easier than going back home and getting more data, which is much more expensive, okay? So it's like trying to think of how you can allocate the different data. Next slide. And so we really explore this for deep neural networks. And in fact, we optimize this kind of data reuse, which we call data flow. How do we move the data through the system, trying to really increase the amount of data reuse? And so by using what we call an efficient row stationary data flow, we can actually exploit reuse, so you can reduce the amount of reads that you get between 100 to 1000x on different levels of the memory hierarchy. And so we realize this with the Iris chip. The Iris chip consumes, a third of a watt of power consumption. Can you click ahead, please? And when you compare it to a mobile GPU, it's actually over 10 times lower energy than a mobile GPU. Again, really focusing on reducing the amount of data movement by exploiting what we call data reuse and sharing data amongst the processing elements. Next slide, please. And so that's from a hardware perspective. From an algorithm perspective, you can also look at, can I just make the neural net itself also more energy efficient? And so one place that we tried to do this was looking at the task of using a neural net to do depth estimation. So given an image, can you predict the depth of each pixel in the image itself? And so as a result, you don't need to use things like time of flight cameras or stereo cameras that can be more expensive. And so we applied a variety of techniques to reduce the cost, the computational cost of the neural network itself. And so in this graph shown here below, right, we have the speed on the x-axis, and on the y-axis, we have the accuracy. And we can see that after applying a bunch of efficient processing approaches to this deep neural network, we can get over a 10x speed up for the same accuracy. Click, please. And so this work was actually presented at a robotics conference last year, and we want to show that you could actually do depth estimation live on an iPhone at 40 frames per second. So this is some of the data that we captured at that conference. And if you're interested in finding more about, fast depth itself, you can refer to the fastdepth.mit.edu. Next slide, please. All right, so there's a lot more to say about, efficient processing of deep neural nets, primarily because deep neural nets are now, so pervasive in a lot of the AI applications. So recently, in collaboration with Joel Emmer, we've written a book on this particular topic. So it's shown here on the left-hand side of the slide, and it's free to download for most institutional subscribers. So if you want to learn a little bit more about this area, I invite you to check out the book. If you are an MIT student, we also offer a course on this topic every spring. So I would invite you to check that out as well at 6812 and 6825. And then also we have just a DNN tutorial website that's free for everyone on the Iris website. And we have various different tutorial slides and papers related to this topic. So if you're interested in learning how to make your neural networks more efficient, I invite you to check out all of this educational material. Next slide, please. Okay, so we talked about robotics and then AI in general for deep neural networks, but let's also think about, what are some applications that can help in terms of health? Because we mentioned that health is another area where we want to do the processing locally. So one particular area that we've been interested in is the idea of monitoring neurodegenerative diseases. So for example, Alzheimer's and Parkinson's. And the sad fact is that dementia affects 50 million people worldwide and continues to grow. Click, next. And so one of the big challenges in this space is the cost of doing these types of assessments, right? So often you need to go see a trained specialist. They'll ask you a series of questions and, for example, do the clock drawing task, right? And the main thing is that you often because you have to go see a trained specialist, it's also often very time consuming. Click forward, please. Also, sorry, go back for a sec. So the other thing is that, so you can't go back very frequently. So the type of a number of measurements you have are quite sparse. They're also mostly qualitative. So depending on which specialist you go to, you might get a different assessment, right? So this can be a very big challenge. Now, next slide, please. And so one of the areas that we've been looking at is, can we quantitatively measure, the state of one person's mental state. And in particular, what they've been shown, it's been super interesting that eye movements are well correlated with these types of diseases. And so if we can measure eye movements, we can quantitatively evaluate the severity and the progression and regression of these various diseases. So for example, you can tell if drug is working or not. And if you can do this, click forward, please. If you can do this on a mobile device, for example, then you can do this within your home. Like a given patient could do this within their home. They could do a lot of repeated measurements, and it would give the physician a lot more information to help with their diagnostics. So this is what we believe is a very promising application of embedded AI. And of course, again, it protects privacy because you're extracting the meaningful information on the local phone itself. Next slide. So next slide, please. Right, so just to summarize, so energy efficient AI really extends the reach of AI beyond the cloud itself. It's a really critical step to make AI ubiquitous. And in order to do that, we need to really look across layers, looking from the algorithms down to specialized hardware. And this is going to be really critical for the progress of AI over the next decade. So really understanding how to traverse the different levels of abstraction. One click, please. And so to find out more about this topic, again, I invite you to visit our group website, and also you can check out updates on our Twitter feed. Next slide, please. And then, of course, we have various talks and tutorials available also on our group website and our YouTube channel. So with that, I'm very happy to take any questions you might have. So I'm not sure where to see the questions. Is it in the chat or?
Yeah, if anyone has questions, please do message in the chat under the event.
And I would say if you want to follow up on any of this stuff, it's on our tutorial website. The slides are also available there as well, since we covered a lot of topics. All right, I cannot tell if there's anything.
I don't think there's been any messages, but okay.
Sounds good. Well, thank you, and hope you all enjoy the rest of the conference.
Yeah, okay, awesome. Thank you, Professor. We're going to close it off here. The next tech talk will be happening in about 5 minutes, so stay tuned. Thank you, Professor.
Thanks.